In heavy manufacturing, thermal energy is a highly volatile physical variable. Without precise management, heat actively fights to destroy the very processes it enables. This graph maps temperature over time. When attempting to reach a set point, initial heat violently overshoots the target. The system overcorrects, oscillating in a hunting wave before stabilizing. These fluctuations carry physical consequences. Overshoots ruin delicate circuit boards, while continuous hunting destroys energy efficiency. To lock variables into a steady state, engineers utilize a massive catalog of specialized hardware. The market is saturated with different form factors, ranging from DIN rail-mounted substrate modules to high-amperage solid-state relays. Navigating this overwhelming hardware selection is simplified by looking at how each component fits into a single, universal architecture. That architecture is the closed-loop PID control circuit. It is the baseline topology governing modern industrial automation. This schematic illustrates the loop. First, the input stage gathers physical data. Second, the logic stage computes mathematical corrections. Finally, the output stage actuates brute electrical power, feeding back into the input. Every piece of hardware simply plugs into one of these three slots. By building this exact circuit from first principles, we can decode the exact capabilities and limitations of the entire industrial catalog. The circuit build begins at the boundary between the digital controller and the physical room. A logic controller cannot correct a thermal error it cannot detect. Engineers capture this data using two primary sensor types. Thermocouples measure heat through the electrical voltage generated at the junction of two dissimilar metals. RTD sensors, or resistance temperature detectors, measure heat by calculating precise changes in electrical resistance across a pure metal element. This diagram outlines exactly where sensors interface. The configuration must perfectly match the probe type on terminals 8 through 12. Engineers must use the exact compensating cable from probe to instrument, or incorrect wire types will actively introduce resistance errors, permanently skewing the baseline. These sensors operate in harsh environments. Sensing heads are typically sealed to an IP65 rating against dust and water, and specific Type K or RTD probes are rated to survive extreme measurement spans, ranging from -200 to over 1300 degrees Celsius. Beyond survival, the sensor must deliver data rapidly. Modern control hardware relies on high-speed sampling times, frequently pulling measurements every 100 milliseconds to maintain a tight, continuous stream of data. That high-speed, high-accuracy measurement is the absolute foundation of the control loop. The mathematics of the logic stage rely entirely on the integrity of the data it receives. That data flows directly into the logic stage, the central processing brain of the circuit, which draws its own power and continuously reads the live sensor input. This equation continuously subtracts the live process value from the target set point to determine the error value. To prevent hunting, the logic utilizes the integral term, adding this deviation to an internal accumulator over time. Increasing the integral action time mathematically smooths the physical reaction. By utilizing this accumulator to analyze historical error, the logic circuit actively anticipates thermal momentum, allowing the controller to eliminate steady-state hunting entirely. The industry houses these identical PID mathematics in vastly different physical topographies to meet the constraints of different factory floors. The baseline standard is the general-purpose panel-mounted controller, featuring a high-contrast LCD for direct manual adjustment by an operator. When the manufacturing process requires automated complexity, engineers install high-performance program controllers. These units execute strict ramp and soak profiles, automatically shifting the set point through multiple phases over hours or days without human intervention. Watch how this panel controller strips away its interface to become a bare substrate-type printed circuit board. Eliminating front panel screens saves space. These faceless logic nodes mount directly into the chassis, communicating with central PLCs via high-speed RS-485 serial networks. Engineers also attach passive devices to these exact same networks. Digital indicators and recorders monitor the data flow strictly to log historical process values and trigger hard safety shutoffs, executing safety logic without actively driving the PID loop. Whether housed in an expensive digital touchscreen or a bare green circuit board, the internal PID mathematics remain identical. The topography changes solely to navigate the physical constraints of the hardware environment. The logic brain calculates exactly what thermal adjustment is required, but a microprocessor lacks the brute electrical force necessary to actually heat an industrial space. This diagram outlines the logic stage's exit point. The controller outputs a weak low-voltage signal through terminals 3, 4, and 5. This delicate logic signal is strictly a command trigger, physically wired to massive secondary peripherals that switch high-voltage mains power. Solid-state relays, or SSRs, serve as the primary actuation peripheral. By using internal semiconductors instead of moving mechanical contacts, an SSR can rapidly switch heavy AC power on and off multiple times per second without suffering physical wear. For systems demanding even tighter tolerances, engineers deploy power regulators. Instead of bluntly switching power fully on and off, regulators utilize phase angle control to smoothly chop the exact AC voltage wave, modulating the raw energy flow continuously. In highly specialized cooling applications, the controller's logic signal triggers a Peltier relay. This peripheral is designed to drive thermoelectric coolers, actively pushing current in both directions to manage rapid heating and cooling simultaneously. These actuation peripherals are the true muscle of the circuit. They form the necessary physical bridge, translating abstract mathematical intent into brute thermal reality. This completed schematic charts the entire dynamic ecosystem in motion. Physical temperature is captured by the sensor, converted into a high-speed data stream for the logic controller, processed through the integral accumulator, and pushed out as a 4 to 20 milliamp signal to a power regulator, which drives the physical thermal load, changing the environment and starting the loop over again. The strength of this architecture is its absolute modularity. Swapping a basic mechanical relay for a high-end power regulator, or replacing a panel meter with a network of substrate boards, does not break the logic loop. It simply scales its physical capabilities. Engineers map the thermal mass, insulation, and dynamic requirements of their unique physical space, and then custom-build a loop component by component to counteract those specific forces. The Industrial Automation Catalog provides the modular physical components required to execute this single mathematical circuit across a wide range of factory environments. True thermal precision results from flawlessly matching the right tier of sensing, logic, and actuation to the specific, unforgiving physics of the process.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.